In this section, we meet Mr. Brooke Taylor and his polynomials. Our goal is to create a polynomial whose behavior near some given x value agrees with the behavior of a random messy function, right? So we don't like messy functions because they're hard to take derivatives of, they're hard to integrate. So if we could create polynomials, which are like sort of the simplest kind of functions to deal with, whose behavior matches our messy function, would make our lives a lot easier. And we've already done a little piece of this in Calc 1 by approximating a polynomial, by approximating our function with a first degree polynomial, or a line, right? So we did this thing called linear approximation, and the linear approximation was just the equation of the tangent line, right? So we had, when you had a random function, you know, curvy and messy, we could say, well, at some particular x value, maybe we'll say it's a in this case, we could approximate that function near a with a tangent line. And you can see that when you're near a, the tangent line is very close to the curve, and it's a good approximation. All right. So we'll just do a quick review on how we find a linear approximation, and then we're going to expand on it. Okay, so I want to find a first degree Taylor polynomial. That just means the equation of the tangent line, a linear approximation, for cosine x. Right, so it's always good to draw a picture of what you're looking for before you start. So here's cosine x. And I want an equation of the tangent line at 0. Right? So this line is what I'm looking for, the equation of that line. We're going to call that P1 of x. So just by looking at it, you could tell me the equation of the line, right? What is it? It's flat, which means its slope is 0, but what's the equation of the line? Y equals 1. Y equals 1. Yep. But let's review how we can get there using calculus, right? So the equation of any line, with the exception of a vertical line, is going to have this y minus y1 equals m times x minus x1 equation. You could also use y equals mx plus b. I just like this one because there's a little less calculation. All right, so the first thing I want is the slope. Anytime you're trying to find the equation of a line, even if you're in an algebra class, you generally start with slope, right? So the slope of that line, the slope of the tangent line is the, everybody? Derivative, yes. Slope of the tangent line is the derivative, right? We repeated it many, many times last semester. So what I need is g prime at that point 0, right? Because the derivative gives you the slope of the tangent line. So I want the derivative at 0. And so first I just need the regular old derivative, right? G prime of x. If g of x is cosine x, what's g prime? Negative sign, right? So what's g prime of 0? 0, yeah. Plug a 0 in there, the sign of 0 is 0. All right, so we've got the slope. We go back to our equation and we say, okay, I can put in a 0 there. And then what I need is a point, an x1, y1. I need a point on that line. So I could use this point, that point that is on the line and on the curve. What is it? What are the coordinates of that point? 0, 1. Yep. You just plug your 0 into your function cosine x, and we get the point 0, 1. That's my x1, y1. So this says y minus 1 equals 0 times x minus 0. And 0 times anything is 0, right? So this says y equals 1 when I move the 1 to the other side. So it's sort of the general procedure for finding a first-degree Taylor polynomial. Okay. We made it so that the function and the line at 0 have the same y value, right? So the function cosine x and this line that I created, they share the point 0, 1. So their function values agree at 0. And we also made it so that the derivative of the line and the derivative of the function also agree at 0, right? So the derivative of the function at 0 is 0. The derivative of this line at 0 is also 0. So that's the idea. We forced the function values to agree, and we first forced the derivatives to agree at 0. So we could take this a step farther by using a quadratic function. Yeah. When you do it at 0, it's a special kind of Taylor polynomial called a Maclaurin polynomial. But I tend to just use the word Taylor all the time. It's the more general. It's not always at 0, but that's the most common center. Okay, so we can take this a step farther by using a quadratic. Instead of a line, we can use a quadratic to approximate the function. So I'm going to do the thing that I did in the first one, make the function values agree, make the first derivatives agree, and then I'm going to also make the second derivatives agree. So that this polynomial I'm going to create, it's going to have the same function value as f. It's going to have the same derivative as f and the same second derivative as f, all at the point 0, at x equals 0. Okay, so I'm going to have some polynomial. So the general form would be ax squared plus bx plus c, right? So I'm looking for a second-degree polynomial that will have the same behavior as cosine x when I'm near 0. So I have 3 parameters to find here, right? I have an a, b, and a c, which means I'm going to need 3 equations, which means I need 3 pieces of information. Those 3 pieces of information are going to be the function value at 0, the derivative of the function at 0, and the second derivative of the function at 0. 3 pieces of information. All right, so let's write, try to do this kind of systematically here. Okay, so g of x, g prime of x, and g double prime of x. So g of x is cosine x, right? What's g prime of x? Negative sine x. Good. And then g double prime is negative cosine x. So then I want to evaluate each of these at x equals 0, because that's where I'm trying to make all these things match. I want to have an approximation near 0. So what's the cosine of 0? 1. Okay, what's the sine of 0? 0, so the negative sign doesn't matter, right? And the cosine of 0 is 1, but I have a negative in front, so this is negative 1. All right, so what I'm trying to do is I want to force the polynomial value, first derivative and second derivative at 0, to be the same as those for g. Okay, so I'm going to calculate, I'm going to write this a little bit smaller. And then I'm going to calculate p2 prime of x and p double prime of x. All right, what is my derivative, the first derivative of ax squared plus bx plus c? 2ax, yeah, plus b. And then my second derivative would just be 2a, just using the power rule. I want to evaluate each of these at x equals 0. When you plug a 0 in for x there, what do you get? Yep. See. When you plug a 0 into x, you get b, right? And when you plug in a 0 here, you get 2a, because 2a is just a constant, doesn't matter what you plug in. And then I'm going to force the polynomial value at 0, which is c, to equal my function value at 0, which is 1. Right? g of 0 was 1. And then the derivative of my polynomial at 0 has to equal the derivative of my function at 0. Right? So b has to be 0. And then the second derivative of my polynomial has to equal the second derivative of my function at 0, which is -1. So to summarize, I'll write it on another page here. I said that g of 0 has to equal my polynomial at 0. G prime of 0 has to be the same as p prime of 0. And g double prime of 0 has to be the same as p double prime of 0. Okay. For the second derivative, when I plug a 0 into my second derivative, you get 2a. When you plug a 0 into the function, you get -1. So 2a has to equal -1, which means that a has to equal -1/2. So I have found values for a, b, and c that will create a function, a quadratic function, whose function value, first derivative value, and second derivative value all agree with cosine x at 0. And it's -1/2 x squared plus 0x plus 1. So those are the a, b, and c values we found. That is this blue function here that I've graphed. So you can see that this quadratic function is a much better model for cosine x near 0 than the line was, right? So this was our linear approximation, and we said a linear approximation can approximate your function if you're really close to 0, right? You know, if I'm like really close to 0, that line is a decent approximation for cosine x. But as soon as I leave that little tiny neighborhood, it starts to be a terrible approximation. But if I use the quadratic, right, I can go much further. I can go much further from x. It's a better approximation for longer. All right, so we can do similar calculations to create a third degree or a fourth degree or an nth degree polynomial that approximates a function. You just force the function value and the first to the nth derivatives at a particular x value to agree with the approximation. So let's say I want to construct a third degree Taylor polynomial to approximate a random function f of x. So I'm not going to use cosine, I'm just going to use a random f near x equals 0. All right, so here's my third degree polynomial. I need to force my first 3 derivatives to agree with the function. All right, so I'm going to take 3 derivatives. The first derivative of this function would be c1 plus 2c2x plus 3c3 x squared. So I'm using c0, c1, c2, and c3 as my unknowns instead of a, b, c, and d. So I took my first derivative, and let's see, my second derivative would be 2c2 plus 6c3x, and my third derivative would be 6c3. All right, then I'm going to evaluate each of these at x equals 0. Right, so I get P3, well, we'll start with P itself. P3 of x, P3 of 0. When you plug 0 into the original polynomial, what do you get? C0, yeah. So the x's all drop out because they're zeros now, and you just get C0. We want to force that to equal f of 0. And then when I plug 0 into my first derivative, P3 prime, I just get C1 And I'm going to force that to be f prime of 0. Okay, I'm going to force my first derivative of my polynomial to equal the first derivative of my function. I'm going to do the same thing for the second and third derivatives. So the second derivative of my polynomial at 0, when I plug in a 0 for x, I get 2c2. I want that to be f double prime of 0. And then this I would have to solve for c2, right? Which means c2 is f double prime of 0 over 2. Just divided both sides by 2 there to get c2. And then I take my p3, triple prime, plug in a 0, and I get 6c3. I'm going to force that to equal f triple prime of 0. So if I want to solve for the coefficient c3, I would just divide both sides by 6. So I have found the 4 coefficients I need to write a cubic polynomial that will approximate f of x near 0. So I could do this every time I want to create a polynomial that approximates a function, but you're going to end up doing the same process over and over and over again. And I can generalize what we just did in number 7 here to this formula, right? So it turns out that your C0, your constant term, always comes out to f of 0. And your coefficient on x, your C1, right, the C1 coefficient on x, always comes out to f prime of 0. So I've got that here, C0, C1x. And then C2 always comes out to f double prime of 0 over 2. And I wrote it as f double prime of 0 over 2 factorial. 2 factorial is 2, right? And then my next one, the coefficient on x cubed, turns out to always be f double prime of 0 over 6. Sorry, f triple prime of 0 over 6. So, and I wrote that 6 as 3 factorial. 3 factorial is 6, right? So if I continued this process, my next coefficient, the coefficient on x to the 4th, will be the 4th derivative at 0 over 4 factorial. So this is the general form for a nth degree Taylor polynomial near x equals 0. Okay, so you can do this for other values, not just 0, but we'll just start with 0 because it's the simplest. Okay. We call P sub n the Taylor polynomial of degree n centered at 0, or about, or around, or near x equals 0. All right, so I'll do this one with you, and then I'm going to have you try one. We want to construct a Taylor polynomial of degree 7 that approximates f of x equals sine x near 0. All right, so I want p sub 7 of x. So I'm just going to copy down this formula for how to find a Taylor polynomial. So I would do f of 0 plus f prime of 0 x plus f double prime of 0 over 2 factorial times x squared. It's the 4th degree. Okay, I'll write really small. And then the 6th derivative over 6 factorial x to the 6th plus the 7th derivative x to the 7th over 7 factorial. All right, so that's what I need to know. I need to now plug in, oh, sorry, those x's. What am I doing? I got to plug zeros in here. That's the... All right, I didn't write them all down. Takes forever. Okay, so I just copied this formula down, right? And I just went up to the 7th degree. So in order to finish the problem, I have to know what f of 0, f prime of 0, f double prime of 0, etc., up to the 7th derivative of f is. And f of x is sine x. So I'll just do that on another page. So I need to know the first derivative through the 7th. Okay, derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of negative sine is negative cosine. The derivative of negative cosine is sine. Derivative of sine is cosine. Derivative of cosine is negative sine. And the derivative of negative sine is negative cosine. And then I have to evaluate each of these at x equals 0. Right? Plug a 0 into each of these, and these will be my coefficients. Right? So sine of 0 is 0. Cosine of 0 is 1. 0, negative 1, 0, 1, 0, negative 1. So those are the f values, f in this first 7 derivatives that I can plug into the formula I wrote on the previous page. Okay, so f of 0 is 0, so I go 0, 1, 0, negative 1. Were people still copying? Sorry. Okay, so we're going to go back to the previous page. F of 0 is 0. So I replace f of 0 with 0. F prime of 0 was 1. So I replace that with a 1, and I still have the x there. F double prime of 0 is 0, so that whole term drops out. F triple prime of 0 is actually negative 1, so I'm going to make that a minus. I'll leave that. And then the fourth derivative was 0. And then the fifth derivative is positive 1. And the sixth derivative is 0. And then the seventh derivative was negative 1. So all I'm doing is replacing the function values, f and all its derivatives, with the values we found. Okay, and then I can get rid of all these terms that have 0 coefficients, and I just end up with x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. 7th degree Taylor polynomial that approximates sine of x near 0. And I drew a picture. I graphed sine of x in black, and then P7 that we just found, that polynomial, is graphed in blue. And you can see it agrees almost negative pi to pi. Right? It's a good approximation. Way better than the linear approximation, which is this guy, right? So the 7th degree approximation expands the region that we can use this to approximate sine. Okay, so now I want you to try one. Construct the 10th degree Taylor polynomial about x equals 0 for the function e to the x. Okay. Once you're done, you'll use your polynomial to approximate the value of e squared, but don't even think about that until you have a polynomial centered at 0, degree 10. All right, so let's go through this together. If f of x is e to the x, what is f prime? E to the x. And what is f double prime? E to the x. And what is f triple prime? Yeah, so this is all of its derivatives. The function is all of its derivatives, right? So that means that f of 0 is e to the 0, which is 1. And that's also what all of the derivatives are at 0. Right? Because every derivative is e to the x, plug 0 in, and you get 1. So all of these coefficients, f of 0, f prime of 0, f double prime of 0, those things are all 1. So this just ends up being 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus blah, 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 all the way up to x to the 10th over 10 factorial. So that function is a polynomial. We love polynomials because they're easy to work with. They're easy to take derivatives, easy to take antiderivatives, although so is e to the x, but still. We like polynomials. So I now have a polynomial that's a really good approximation for e to the x. And in fact, that means that e squared should be able to be approximated by the 10th degree Taylor polynomial evaluated at 2. So if I plug a 2 into that polynomial, I should get something that approximates e squared. So let's... Okay, luckily I have this all written out already. I typed... Yeah, it's like one of those cooking shows, yeah. I typed this whole function, 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24. And I did all the factorials I knew in my head, and then I started using the factorial button. Yeah, it's in your math menu. So if you press math and then move your cursor to the right to PRB, it stands for probability. Option 4 is factorial. First, you have to put the number, yes. So if I want 6 factorial, I type 6. Math over, number 4, and hit enter, and it tells me it's 720. So I typed that whole 10th degree polynomial in here. I'm going to quit out of here, and I'm going to check e squared. I'm going to have my calculator do e squared. And it says that it's about 7.389. Then I'm going to have my polynomial estimate e squared by plugging a 2 into that polynomial. So I'm going to do vars, y vars, function 1, evaluated at 2. And we have a really good approximation. Agrees to 2 decimal places. And I think I forgot to do that on the last problem. I was also supposed to... Yeah, I was supposed to use this P7 that we found to approximate the sine of pi over 3. So I'll just do that. The sine of pi over 3 should be able to be approximated by P7 of pi over 3. And so I'm just going to... We all know that the sine of pi over 3 is root 3 over 2, right? And we've plugged that into our calculator so many times, you know that that's about 0.866. But I'll type it in anyway. Sine of pi over 3, oops, is about 0.866, right? All right, so I'm going to plug a pi over 3 into this polynomial. So maybe I'll just put that in like y2. So I'm going to have x minus x cubed over 6 plus x to the 5th over 120 minus x to the 7th, oops, x to the 7th divided by 7. I don't know 7 factorial off the top of my head, so I'm going to put factorial. So that's my polynomial, my 7th degree Taylor polynomial. And then I'm going to do vars, y vars, function y2, and plug in a pi over 3. and I get about 0.866. I get a really, really good approximation. This is actually how your calculator does, how it finds values of sine and cosine and log and e. It uses polynomials, right? Because your calculator can, otherwise it would have to use tables or it would have to know the unit circle, right? This is what your calculator does. Because root 3 over 2 is an irrational number, and there is no decimal that's exact, right? Yeah, it depends. It depends on what you ask it to do. Yeah. Yeah. Yeah, it would. I get what you're saying now. Why is it different? Not why is it not exact? They're different because your calculator is using a higher degree polynomial than we just used. So here are several Taylor polynomials approximating e to the x. So e to the x is graphed in black here. And we've got the first degree Taylor polynomial, the linear approximation that we learned how to do last semester. And then we've got a quadratic and a cubic and a quartic, and each one is getting closer and closer and closer to that function e to the x. So you can see that as the degree of the approximating polynomial increases, the approximation to the function gets better. So we can also construct Taylor polynomials that are centered at x values other than 0. So in all of our pictures, we have forced everything to agree at 0, right? For e to the x that I just, oops, where's my e to the x? E to the x, everything agrees at 0. All of my approximating functions touch at 0 and then get closer and closer and closer. So 0 is called the center, right? But I could center it anywhere else also. Okay, so I could center it at any x value other than 0. We'll call it a. And this is the Taylor polynomial centered at a. You can just think of it as like a horizontal shift to the right a units, right? So instead of zeros, I have a's. And if a were 0, this would say x minus 0, and it would just collapse to an x. All right, so I'm going to let you try to find a Taylor polynomial of degree 4 that approximates the function ln x near x equals 1, right? So you're going to use the formula above, but a is going to be 1 this time instead of 0. All right, let's finish this together. So all I did in this first step here that I wrote down was I copied this formula for p sub n of x, and I replaced all my a's with 1s because they told me that this thing is going to be for x's near 1 or centered at 1. All right, so all I did was copy this down and replace all my a's with 1s. And then as I'm looking at this, I say, okay, if I want to simplify this, if I want to finish the problem, I have to evaluate f of 1, f prime of 1, f double prime of 1, f triple prime of 1, and the fourth derivative of f at 1. And f of x is ln x, right? So I'm going to write down my derivatives here, which means that f prime of x, derivative of ln is 1 over x, and f double prime is negative 1 over x squared. Just do the power rule. And f triple prime is 2 over x cubed. And my fourth derivative is negative 6 over x to the fourth. And then I have to evaluate all of these at 1, right? That's why I started doing these, so I could get f of 1 and f prime of 1. Okay, so at x equals 1. So the ln of 1 is 0. And 1 over 1 is 1. Negative 1 over 1 squared is negative 1. 2 over 1 cubed is 2. And negative 6 over 1 is negative 6. Those are my coefficients. Those are my function and derivative values. So I go back up here, And I'm just going to replace those function and derivative values with what I got here. So I got 0 plus 1 times x minus 1 plus minus, because that's a negative 1, minus 1 times x minus 1 squared over 2 factorial, and then plus 2 times x minus 1 cubed over 3 factorial, minus 6 times x minus 1 to the 4th over 4 factorial. There's my 4th degree Taylor polynomial for ln x, centered at 1. Make sense? All right, so I'm going to give you another one to try now that we've gone through one together. Skip the challenge for now. If we have time, we'll come back. Find the Taylor polynomial for the function cosine x, but instead of centering at 0 like we did earlier, center it at pi. So you want to find the Taylor polynomial of degree 6 near x equals pi. Together. All right, so in this case, because they said near x equals pi, that's my a. A is pi. So all I have written down here so far is the formula for a Taylor polynomial, right? The general formula that I gave you on the previous page. But in this case, a is pi. So I'm going to plug pi's in for all of these things. And I just stopped at degree 6, right? So this is going to be f of pi plus f prime of pi times x minus pi. So I'm just replacing all the a's with pi's. Plus f double prime of pi times x minus pi squared over 2 factorial plus f triple prime of pi times x minus pi cubed over 3 factorial. And I don't want to keep writing these. I'm going to go to the 6th derivative evaluated at pi times x minus pi to the 6th over 6 factorial. So what I need to know is I need to know the function and its first 6 derivatives evaluated at pi. I don't really have enough room here, so I'll do it on another page. So my function is cosine x. And I need the first 6 derivatives. Hold on, I'm not ready to write them yet. All right, the derivative of cosine, negative sine. Derivative of negative sine is negative cosine. The derivative of cosine with no negative sign would be negative sine. So you have negative negative sine, which is just sine. Derivative of sine is cosine. Derivative of cosine is negative sine. And the derivative of negative sine is negative cosine. Then I have to evaluate all of these at x equals what? Pi, yeah. Evaluate all of them at the a value that you're working with. So the cosine of pi is negative 1. Sine of pi is 0. Positive 1, 0, 1, 0, positive 1. So a bunch of my terms are going to drop out because it looks like my odd derivatives, the 1st, 3rd, and 5th, are 0. So those terms are all just going to drop out because 0 times anything is 0. So I go back to my formula, all my odd derivatives of f come out to be 0. So this term is just 0, this term is 0, and there's a 5th degree term in there that's 0. And then I just plug in the rest of the stuff that I calculated. So f of pi, that was negative 1. F double prime of pi is positive 1. So I have 1 over 2 factorial times x minus pi squared. And then my 4th degree term was a minus. Yeah, so I have negative 1 over 4 factorial times x minus pi to the 4th. And then my 6th degree was positive 1. So I have 1 over 6 factorial x minus pi to the 6th. So there's my 6th degree Taylor polynomial for cosine x. centered at pi, centered at pi. All right, so I'm going to show you a quick animation. I want to show you several Taylor polynomials that are going to approximate cosine x at pi. So the first one is a first degree Taylor polynomial, which is just the line, right? And we learned how to do this in Calc 1. Okay, so then my next one, the second degree, is a quadratic. And then the third degree is nothing because the third degree drops out. Right? The coefficient was 0. And then I have fourth degree, and sixth degree is the one we just found. So this one in brown is the sixth degree. So you can see how they get better and better. This line is, compared to the others, terrible, right? It approximates the function cosine x only when you're really, really close to pi. But the quadratic goes much further, and then the quartic goes even further than that, and then the sixth degree one looks like it goes almost from 0 to 2 pi. We have really good agreement. Okay, so we use Taylor polynomials for a couple of things. You can use it to estimate the value of a function, and it was used a lot for this before calculators, and it's actually how calculators do this. So if I wanted to evaluate the ln of 1.1, I could go back to my work on number 13, where I found a Taylor polynomial for the ln of x near 1, and I could try to plug a 1.1 into it. And we'll just do a little bit of that. I'm going to get it on a new page here. Okay, so this is ln of x is approximately equal to that Taylor polynomial when I'm near 1, right? Near x equals 1, those things are approximately the same. So I could say the ln of 1.1 is approximately equal to 1 times 1.1 minus 1 is 0.1, minus 1 times 0.1 squared is 0.01, 0.1 cubed is 0.001, and 0.1 to the fourth is 0.0001. And all of those calculations are relatively easy, right? Because you're just dealing with powers of 10, you know, moving decimal places over and stuff. So we could do this in our heads if we really wanted to. I don't really want to because we're running short on time. So you get the idea. This is how your calculator evaluates these things. All right, and then how could we get a better approximation for ln of 1.1 than what we just did? Yes, he's a calculator. What does your calculator do to get a better approximation? A higher degree. Yeah, a higher degree Taylor polynomial. Okay, so here's where Taylor polynomials come in really handy, and it's with integrals, because you may have realized that of the vast functions out in the world, we can only integrate, we can only find an antiderivative for a teeny tiny fraction of them, right? So we've learned all these techniques, and it's a lot of really hard work, but even with all the techniques that we've developed, there's still lots and lots of functions we can't find an antiderivative for. For example, sine x over x. We have no technique that will help us find an antiderivative for that. So what I could do instead is use a Taylor polynomial that approximates sine of x and plug in there. So instead of doing the integral from 0 to 1 of sine x over x dx, because no matter how hard I work, I cannot find an antiderivative for this thing. Instead, I'll do the integral from 0 to 1, and I'll replace sine of x with a Taylor polynomial that closely approximates it near 0. Since I'm only going from 0 to 1, this should do, right? It should really closely match sine of x from 0 to 1. So I'm going to have x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial all over x. So an approximation for sine of x over x. I can divide that x in. It can divide it into every term. So I'm going to have 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial minus x to the 6th over 7 factorial. And now this is so easy to integrate, right? This is just the power rule 4 times. And I'm out of room, so I'm going to do it on another page. So now taking the antiderivative is not so hard, right? So the antiderivative of 1 is x. The antiderivative of x squared is x cubed over 3. So this is going to be minus x cubed over 3 times 3 factorial. Plus the antiderivative of x to the 4th would be an x to the 5th over 5. So I have a 5 times 5 factorial. And then minus x to the 7th over 7 times 7 factorial, evaluated from 0 to 1. So I can just plug in a 1 because when I plug in 0, everything goes away because every term has an x. So this is just going to be 1 minus 1 over, all of these numerators are just 1s too. 3 factorial is 6 times 3 is 18. Plus 1 over 5 factorial is 120 times 5 is 600 minus 1 over 7 factorial, I don't know in my head. Seven factorial times 7 is 35,280. Yeah, just checking. Okay, so then I add these up. 1 minus an 18th plus a 600th minus 1 over 35,280. And I get 0.946. So now I have a method for approximating these things myself without relying on technology. Right, so I'll just use the technology to see if I come out with the same thing. So it was math 9, and then I'm going to put my function sine x over x, comma 0, comma 1, or whatever Wolfram you're going to use or whatever, 0.946.